That's an I. It is. All right. So our last lesson is calorimetry. Calor sounds and looks a lot like calorie. Means heat. So when we talk about calories, like in your diet, like what you eat, calorie is a measure of, if you're talking about food, it's a measure of how much energy that food has. It's the amount of energy to raise 1 gram of water by 1 degree Celsius. That's actually what a calorie is. And you guys actually know the value of a calorie as well. We've been working with it for 2 weeks now. We'll work with it again today. But anyway, for calorimetry, let's start off with what you need. What you need for a calorimetry device. A, you need an insulated environment. We call that the calorimeter. Now, it could be some big, really cool, big, expensive, well thought out device. Sometimes it is. Or it could be something really, really simple, like next week, we will use a styrofoam cup, which is it's good, it's fine, it's an insulated device, it works just fine. So there's our styrofoam cup. Hopefully you've all seen a styrofoam cup in your life. That's our calorimeter. Again, styrofoam is an excellent insulator. So that's what you need. That's our calorimeter. You also need water. Well, I'll be honest with you, I'm not sure if you have to use water. In fact, you probably don't. But I think we usually do. It's easy, it's simple, and then primarily, intruder got me. So water, because we know it's specific heat. Again, we measure that in C. You guys have seen that before. Specific heat is measured in C. So there's our water. It's in our calorimeter. It's in our styrofoam cup. And then lastly, you need sorry. Lastly, you need an object that you want to know what the specific heat is. That can be whatever object you'd like. We often use a piece of metal, but it can be anything. Anything that you can put into that water, you can use as your object. Again, usually we use like a metal cylinder. This is our object. We'll call it metal cylinder. But again, it doesn't have to be metal. Again, I guess necessarily this doesn't have to be water, but I've never seen a calorimeter that doesn't use water. But I guess it doesn't have to use water. You got your metal object, you've got your calorimeter, you've got your water. here's the theory behind a calorimeter and doing calorimetry. So here's the theory. Not much to it, to be honest with you. The theory is that whatever energy you have in your insulated cup, your calorimeter, doesn't change. It is a closed environment. It does not gain heat from outside. It does not lose heat to the outside. The overall energy in the calorimeter does not change. Now, is that perfect? No, there's no perfect cooler anywhere. Yeti might disagree, but I don't care. They're wrong. So it's not perfect theory, but it's really sound. You can have this insulated environment. Heat will not leave it. Heat will not go into it. So the amount of energy that you have doesn't change. I'm going to use the word object instead of metal. Again, we usually use a metal, but it doesn't have to be a metal. It can be any object you like. So the idea is we can measure the temperature change of the water. And then big point here, big point. A lot of times people confuse heat, which is energy, with temperature. And they're completely different things. Temperature and heat are not the same thing. Not the same thing. They're related. You need temperature to solve for heat, but they're not the same thing. So the idea is if you can measure the temperature change of the water, like let's say I start with really, really cold water and I have a hot piece of metal, very warm piece of metal. When I put that warm piece of metal into the cold water, the water is going to go up. Temperature is going to change. If I can measure how much it changes by, I can calculate the heat gained by the water. And again, because we were working in a closed system, whatever heat that was gained by the water must be the same heat lost by the metal, and I can figure out a lot about that metal that way. That's the idea, that's the theory behind calorimetry. We're going to put a warm metal into the cold water, or you could do it vice versa. You could have warm water and put a piece of cold metal in. Either way works. The energy that is lost by the water is the exact same energy gained by the metal. Heat is not escaping. That is an insulated container called the calorimeter. Heat is not escaping, so any heat transfer must have just occurred between the water and the metal. Q must equal Q, but they're opposite. That's a negative sign. They're opposite. The formula, of course, working with formula, of course. The Q of the object, so again, Q is how we measure energy or heat, is equal to the negative Q of the water. That's as simple as it is. Excuse me, I shouldn't say the negative Q of the water, the opposite of the Q of water. The water might gain energy, it's just the opposite of the object. The water's gaining, the object's losing. Not necessarily a negative sign so much as it is an opposite of sign. Hey, we know what these Q's are. We know how to find Q. We've been doing that for like 2 weeks now. We have a temperature change. So our formula for Q when we have a temperature change is the mass of the object, got a little O there for object, times specific heat of the object, times the temperature change of the object. Remember this formula? Mass times specific heat times temperature change is equal to Q. Well, if I substitute this in for the Q of the object, I can set that equal to the opposite Q of the water, which we find in the exact same way. The mass of the water times specific heat of the water times the temperature change of the water. And again, I got the whole thing inside parentheses because I've got the opposite of right here. They're equal but opposites. Questions so far? Good so far? Got to flip the page, so good time to pause, check for questions, so that we get caught up here if you need to. Everyone's good? Cool. Well, let's see how this works in action, huh? All right, so here's what your homework looks like tonight. Here's a sample type of problem of calorimetry. So 41.65 gram sample of metal at 100 degrees Celsius is placed in a 125 grams of water at 25 degrees Celsius. The final temperature of the system is 30 degrees Celsius, and they want us to determine the specific heat of the metal. Okay, so this is what we got to do. I like to list up my variables. You guys know that. I cannot recommend this enough. So the mass of the metal, 41.65 grams. The specific heat of the metal. That's the unknown. That's what we're trying to solve for. That one gets a question mark. And I'm going to need the temperature change of my metal. How do I know I need all this stuff? Well, the formula we just took a look at, there's the three things. Well, I'm just using metal instead of object. My object in this case is metal. So M for metal. All right, well, the temperature change, guys, this is really important. Always, always, always final minus initial. Why is that so important? Well, because you're going to have some negative signs. And that's okay, you should, but you have to have the right number of negative signs because you don't want a negative specific heat. That's not a thing as far as I'm aware. You don't want a negative mass. Not a thing as far as I'm aware. So watch your negative signs. Always do final minus initial. Our final temperature is 30 degrees Celsius. Our initial temperature of our metal is 100 degrees Celsius. So final minus initial means that my temperature change is negative 70 degrees Celsius. My metal has a negative 70 degree temperature change. All right, next up, my mass of water, W for water, mass W, 125 grams of water. Specific heat of water. This one we know. We've been working with this for like 2 weeks now. .18 joules per gram Celsius. Hey, guess what? That's also a calorie. It's numeric value for a calorie. It takes 4.18 joules of energy to raise 1 gram of water by 1 degree Celsius. Now look at all this learning you guys are doing today. And finally, then we need the temperature change. Again, final minus initial. The whole system has a final temperature of 30.0 degrees Celsius. The initial temperature of the water, 25 degrees Celsius. So the water changes by 5 degrees Celsius. Hey, notice I've actually lost a significant digit there. This is another one of those reasons why it's important to show your work and your steps, even something as small and insignificant as that. A lot of times people don't show all their work and they don't realize that, hey, we're down to just 2 significant digits there, even though every number up here has at least 3 or even 4. That is going to affect our final answer. So watch that. Watch that. Again, that's fine that we're down to that many. It's a subtraction step. Subtraction and addition, it matters where the last sig fig is at, 10ths column. It doesn't matter how many total you have. So the fact that we're down to just 2 is perfectly all right, and it's actually how it should be. Okay, let's take a look at how we're going to solve this. Again, our Q's are equal to one another. The Q lost by the metal is the exact same Q gained by the water. So So the mass of our metal times specific heat of our metal times change in temperature of our metal equals the opposite of the mass of the water times specific heat of water times change in temperature of the water. So there's my formula. Again, I highly recommend. I know a lot of you aren't doing it and you're messing up with your algebra sometimes. It happens. This helps with mathematical concepts to rearrange your variables. Isolate the one you're going for. We're trying to solve for C of M. That's our question mark. Let's get that on the side by itself. How do we do that? Well, right now it's mass times C times delta T. Opposite of times is divide. So we need to divide both sides by the mass and the change in temperature. Cool. There we go. Now we're ready to plug things in. I've got all of these. Okay. I'm looking for that. So let's write down our numbers and solve. The mass of my water is 125 grams. Specific heat of the water, 4.18 joules per gram degree Celsius. And my change in temperature of my water was 5.0 degrees Celsius. I'm going to divide all that by the mass of my metal, 41.65 grams. And the temperature change of my metal, negative 70.0 degrees Celsius. And watch your negative signs. The way I'm going to enter this into my calculator, don't know that. So the way I'm going to enter this into my calculator is I'm going to start with the negative sign, and then I'm going to open up a parentheses. I'm going to do my math exactly like I see it. 125 times 4.18 times 5.0. Now I'm going to close my parentheses. And I'm going to hit divided by 41.65. And then, because I say this all the time, I'm still getting some of you guys not doing it right. Divided by negative 70. I know that's a time symbol. I get it. You guys are so eager to hit the time symbol. But guys, this number's on the bottom. It is divided by right there, not times. Quit hitting the time symbol. It's on the bottom. My negative. Press enter, and voila. There we go. This is a great answer. Metals have very low specific heats. Waters is pretty high. Metals are pretty low. So a decimal for a value for a metal is probably what you should be looking for. In fact, this is even relatively high for a metal. Some metals are as low as 0.4, 0.3, sometimes even 0.2. So this is good. So my specific heat for my metal, let's check for digits here. I've got 3 there, only 2. Hey, that subtraction step we showed came back in a big way. 4 and 3, we're limited to just 2 with that multiplication. So the 8 is the first one, the 9, we look at the number after the 9, it's enough to round up. 0.90 is appropriate significant digits. Zeros to the left of the number never count. Let's take a look at our units then. Well, grams divides out. Degree Celsius divides out. We're left with joules per gram degree Celsius. Cool, sweet. That's exactly the way we needed it. That is the unit for specific heat, so that's perfect. There we go. So again, metals tend to have very low specific heats. You guys have probably noticed this without really thinking about it. Like for instance, have you guys ever been to an outdoor sporting event or something like that with metal bleachers? Maybe you go to the football game And when you first get there, it's still light out. It's it's late afternoon, and the bleachers might be kind of warm because the sun's hitting on them and they're warmed up. By nighttime, though, the sun is set. It's a little cooler out. The game's over. It's nighttime, and now if you sit down, the bleachers are freezing cold. That quick temperature change has to do with these tiny little specific heats. Small specific heat means it's easy to change temperature versus water. Water actually is a pretty big specific heat. 4, that's a pretty large specific heat. It's a lot more difficult to change the temperature of water. That's why, especially this time of year, you might go outside, might be like 75, 80 degrees outside, and you run, you jump in the lake, and it's still really cold water. Because water takes a lot longer to warm up than metal, or even air for that matter, or you. Water's got a large specific heat, so it takes a long time to warm up. On the flip side of that, though, in October, you might get a chilly day outside, but the lake water is still kind of warm. Like, wow, that's surprising. The water's warmer than the air. Why is that? Well, exact same thing. That water's going to lose its heat a lot slower as well. So that big number there means it's kind of resistant to gaining or losing heat. Metals, generally small. Fractions. Questions?